So for this lesson, this is the first of two parts. Let's discuss the motion of particles through fluids. So let's take these as examples on the right. So if motionless, there are two forces acting on the body in a fluid. That's weight and the buoyant force. However, if it's moving, so for a rigid particle moving through a fluid, there are three forces acting on the body. The external force, which is the force of weight. So F external is mg over gc, correction factor. The buoyant force, which is opposite but parallel in direction to the external. And lastly, the drag force. So opposite also of the direction of motion. And then, of course, after it has overcome all these, like it could reach its what you call terminal velocity. So let's consider a particle of mass m moving through a fluid under the action of an external force. So if we do the mass balance, diba, the mass times acceleration, the force overall, let the velocity of the particle relative to the fluid be u. So this would be mass times acceleration is equal to in the direction of the motion. So that's the weight minus the buoyant force minus the drag force. And as I have said earlier, the external, let's just say that that's mass times acceleration due to gravity in this case. The buoyant force would be, based on Archimedes' law, the product of the mass of the fluid displaced by the particle and the acceleration from the external force. So the volume of the particle is mass over density. So mass of the particle over density of the particle. And whereas the mass of the fluid displaced is mass times yung ratio niya ng mga densities. Kasi 'di ba, basically this is density over density magka-cancel, it's just mass. So when the density of the fluid or the density fluid, the buoyant force is given by this equation. So you can see in here the streamlines. So for example, let's just say these are the direction, di ba, ng velocity. This is the projection or the projected area of the sphere in here. You can see that there is distortion. There is distortion in the velocity. So nag-change ng velocity and then, di ba parang if you can recall yung mga sa airplane, yung mga aerodynamics, right? Just like that, there would be locations wherein the speed would be slower, there would be locations wherein the speed would be faster. So those are the fluid streamlines. So the drag force can be solved by this one. Drag force is CD U squared rho AP over GC. So in this case, I'm just writing the correction factor as red. So if it's SI units, there's no need for this. Again, what is CD? CD is the drag coefficient. AP is the projected area, just like this, of the particle in the plane perpendicular to the flow direction. So for a sphere, the projection or the projected area would be a circle. So it's just pi r squared or pi d squared over 4. Whereas for the cylinder, if it's a cylinder horizontally configured, what happens is you will see a circle. So it's pi d squared over 4 as well. Where if it's a vertical cylinder, for a vertical cylinder, you will see in here basically like a rectangle. So length times the diameter of the particle. So length times width, right? So in here you can see the different lines. So again, for sphere, di ba, the flow is perpendicular always to the surface, to the projected area. For the sphere, for a disk and a cylinder, take note that the solid lines, the drag coefficient as a function of Reynolds number. The x-axis is Reynolds number. The y-axis is the drag coefficient. What can you say is the relationship between the drag coefficient and the Reynolds number? As the Reynolds number or as the flow becomes turbulent, what happens to the drag coefficient? may sudden decrease, and then it increases as well after a certain point in time. So you can see here the continuous line is for the sphere, the dashed line is for the disks, and then the chain dashed line, so this one, the one with circles in between, is for cylinders. So what you can see in here is that at a Reynolds number of 100 or less, typically the one that has the highest drag coefficient are the spheres, and then the lowest is this one, the cylindrical. Whereas what will happen is as it reaches, greater than 100 Reynolds number, there's sudden decrease in the sphere, and then the others are left above. Pero as you have said, around 10 or 5 to the 5 times 10 to the 5, there's a sudden decrease. So it is essential to know the terminal velocity of the particle. Sorry. So for the terminal velocity, again, with this equation, you can divide everything by the mass. Take note that this is m times AE, so just divide by m, you're left with AE. This one, due to the buoyant force, MAE, and then times, so this one is density of the fluid over density of the particle, minus the drag coefficient, u squared, so everything is divided by m here. So only the last term is the one that would be containing m. And then if we combine the first two terms and then factored out AE, you'll end up with this. So let us take two cases for the terminal velocity. First is motion from gravitational force. In the event when the external force acting on the object is only gravitational in nature, AE would be equal to G, or the 9.81. You know that. So I can just replace AE by G. No problem. Whereas if the motion is found in a centrifugal field, G would be, basically it will just be a factor of G, the acceleration. So it can be 2G, 3G, 4G, 5G, 2.5G, so on. So take note also that if it's centrifugal in nature, take note that there's what you call the angular velocity, right? So what is R in here in this formula? R is the radius of path of the particles. But of course, in a circular field or centrifugal motion, you would have omega, the angular velocity in radians per second. So take note of those. In gravitational settling, G is constant. The drag coefficient always increases with velocity. And the acceleration, A, decreases with time and approaches zero. The particle quickly reaches a constant velocity, which is the maximum attainable under circumstances. So guys, if you were to say that when the maximum settling velocity is reached, remember that when you get the maxima or minima, the derivative, becomes zero. So there's no more acceleration in here. It's not accelerating anymore. You can equate that to zero, and then you can see that in order to solve for ut, that u in here becomes a terminal velocity. So you can combine them, and then you'd be able to solve for u as the square root of 2g, density of the particle minus density of the fluid times mass all over projected area, density of the particle, drag coefficient, and density of the fluid. Next, take note of this. Taking this into consideration, for spherical particle of diameter dp moving through the fluid, the terminal velocity is given by this one. It can be simplified into this. How? Take note that mass is 1/6 pi dp cube density, and that the projected area is 1/4 pi dp to the 4. So substituting these in place of ap and m, you'd be able to simplify it in this form. So this one, do take note of this formula. Okay? So the other one is gravitational. This one. In motion from a centrifugal force, so again, taking note of the general equation for terminal velocity, the velocity depends on the radius. The acceleration is not constant if the particle is in motion with respect to the fluid. So in many practical use, the centrifugal force, it's so small wherein this one basically is again approximated to zero. Thus, it can be neglected, giving rise to this. So here, you'd be able to see the difference between this term and the other term. So please do take note of this as your other equation. Now, in order to solve for the terminal velocities in here, you can see that there are CD terms. CD again, they are drag coefficients. So what are those? Drag coefficient is a function of Reynolds number. The drag curve applies only under restricted conditions. So what are those conditions? Number one, the particle must be far from other particles and that the vessel wall, so that the flow pattern around the particle is not distorted. That's why you can see in here that as you go near this particle, the motion becomes distorted. So if there is a particle that's a bit close, let's just say in here, if there's another particle that's a bit close to this, the motion would be already distorted. And then it should be not against or not near the walls. Why? For example, you are near the wall, say these are the walls. You have to remember that the motion would be something like this, right? The velocity would be bigger or biggest in the middle, and then it would have friction on the sides. So it's a bit smaller as it goes nearer and nearer the sides. Can you understand? Number two, it must be moving at its terminal velocity with respect to the fluid for you to consider the drag coefficient. So there are actually several figures, figure 7.3, 7.6, and 7.7 from McCabe, 652 from your handbook 9th edition. These will be provided to you. So an example is the one I showed you earlier. This one is one of the examples of Reynolds number and drag coefficient correlation. So this one is basically spheres, disks, and cylinders. The only problem is that this one from 1, 3, 4, 5, 6. So that means ang count nito is zero point 0.2, zero point 0.4. So every 2 ang count niya. It's the graduation is not very sensitive. This one might be a bit better or roughly the same. Roughly the same siya. Oh. 2 kasi you have to take note that this is in logarithmic scale. So what will you be able to notice in those figures also? Let's go to the particle, the property, the Reynolds number of the particle. Take note, you already know the formula for Reynolds number. D velocity rho over mu. Okay? Now, what type of viscosity is this, mu? Because there are two types of viscosity, right? Can you tell me what type of viscosity is this? Kinematic viscosity. So, for the Reynolds number, if the Reynolds number is less than 1, Stokes' law applies. It's laminar flow. So, what are the relationships that we can use? The CD could be approximated by 24 divided by Reynolds number of the particle. And then the drag force is 3 pi terminal velocity and diameter. What is this one? Anong klaseng viscosity versus this? The first one is what type of viscosity? The first is dynamic yung mu, tama? This is kinematic. So the thing is, eventually you might you might encounter both given in the test. The thing is, how do you, parang which one will you be using? Let's see. So in here, after substituting these, you'd be able to solve for the UT. This is the general form, general equation of the terminal velocity. GdP squared, density of the particle minus density of the fluid over 18 mu. Now, again, these are some of the formulas here to come up with this, to simplify that. Do take note, guys, that this one, for the Reynolds number, apart from the density of the particle and the terminal velocity of the particle, the rest are for the fluid. Of course, di ba? The viscosity of the fluid where it is moving, and then the density of the fluid at which it is in. So that's the Reynolds number, right? Now, this one is for Stokes' law. This one, the next one, if it's greater than 1,000 but less than 200,000, it's turbulent flow. So for turbulent flow, Newton's law applies. So we can approximate the CD to be 0.44 and then the drag force to be this formula. So that means for the terminal velocity, there is another formula. So we can have here, let's just call this formula number 1 for the terminal velocity. Let's call this formula number 2. Formula number 2 for terminal velocity. So Newton's law applies to fairly large particles falling in gaseous or low viscosity fluids. Whereas lastly, in here, to identify the range in which the motion of particles lies, the velocity term is eliminated from the Reynolds number by substituting the terminal velocity from Stokes' law. So you can see that using Stokes' law, you already have this, right? Kasi these two, basically, just to show how do we solve for CD, right? How do we solve for UT? By characterizing using the Reynolds number. But there are what you call criteria to know which settling regime is. So there are three in here, you will notice. There would be three. So using Stokes' law, UT, again, this one, and then using the formula for Reynolds number, so just plug in the UT in place. Determine to determine the settling regime, a convenient criterion K is introduced. So it's this one. K would have the formula dP, G, rho of the fluid, rho of the particle minus rho of the fluid, all over mu of the fluid squared. And then this term is raised to 1/3. However, if Re, the Reynolds number, is approximated to be 1, solving for K, this one would be 1, that's 18. The cube root of 18 would give you 2.6. So I can safely say that if the K is less than 2.6, that means Re would be less than 1. So Stokes' law applies in here, in these formulas. So for Newton's law, UT is 1.75 as I have given you earlier. By substitution, K would have this form. It's the same form, right? Again, if Reynolds number is taken to be 1,000, you can solve for K. It gives us 68.9. Whereas if R is 200,000, it would give us a K that has a value of 2,360. Again, diba, these are the cut-off values kasi that we used earlier. Whereas summary, look at this. Stokes' law range is when Reynolds number is less than 1 or when K is less than 2.6. Newton's law range is when Re is greater than 100 but less than 200,000, or when K value is 68.9 and less than 2360. Whereas if it's greater than 2.6 but less than 68.9, or when it is much greater than 2360, it is found UT can be in this form, just the general equation. This one. Kasi di ba I gave you first formula ng UT, second formula, this would be the third formula. That one here. Tama, di ba? O yan. The first, second, third. Okay. Using a value CD found from here. Found from here. Again, this is one of the CD versus Reynolds number curve. So, in general case, the terminal velocity UT can be found by trial and error. After guessing Reynolds number, to get an initial estimate of the drag coefficient CD. So normally in this case, the particle diameter is known. So in here, you can see that this is just representative of the Stokes law. This one's representative of the Newton's law, and this one, crushed limestone. But then for spherical structures, we approximate it to be spherical, especially if it's stated naman it's spherical.